We're going to start with a little quiz now, and in these two lectures, by the way, we will be giving you a lot of little quizzes, so keep a piece of paper out and be able to stop the tape at each point so that you can give it a try yourself before I give you the answer. So here's the first structure, and stop the tape at any point at this point and write down what you think the answer is, and then I'll tell you what the answer is. So first of all, you want a number, and again you want a number to lower to the lowest, to keep the numbers as small as possible. So you start from the right and move to the left, and you have four carbons. Now a 4-carbon chain is called butane, and so you start out at the bottom, you have the name butane, and then you have a chlorine at the 1 position and a bromine at the 2 position, and so this is 1-chloro 2-bromo butane, and it's written just like it's shown on the slide. Let's try another one. Again, stop the tape and give it a try yourself, and then start the tape and I'll give you the answer. Okay, first of all, if you count without lifting your pencil, you end up with 5 carbons, and 5 carbons is pentane. Then, to get the numbers as small as possible, you're going to start from the right again. So you have 1, 2, and there's an iodine, and 3, there are 2 bromines, and that's it. So it's 2 iodo, and then 2 3s, 3 3, because that says that each bromine is, both of the bromines are on the 3 carbon, 3 3 dibromo pentane. Now, a side group that's not just a simple chlorine or bromine is called an alkyl group, and this is a group that has 1 less carbon than an alkane and is attached to the long chain at some point. And so methane, the alkyl group, would be methyl, and ethane, the alkyl group, would be ethyl. And so, for example, here we have a structure that has, if you start either from the right or the left and draw, you can see that you can draw across 6 carbons, or you can go from where it says 6 to 3 and then draw up, and you still have 6 carbons. And so no matter how you draw it, the longest chain that you're going to get is a 6-carbon chain, and so it's hexane. And again, you're going to number from right to left, because if you number from left to right, you end up with 4 ethyl hexane. You don't want that. You want as small as numbers possible. And so it would be 3 ethyl, it's ethyl because it's 2 carbons, 3 ethyl hexane. So why don't you give this one a try? Stop the video and write down what you think it is, and then I'll go over what it is. Okay, if you take the top structure and draw a line from left to right, you see that you have 8 carbons. And if you start with the side chain, the longest chain you can draw starting with the side chain is also 8 carbons. And so it's 8 carbons. You're going to number from right to left this time, because if you number the other way, from left to right, you end up with a 5 instead of a 4. And this is a 3-carbon alkyl group, so this is called propyl. A 3-carbon alkyl group is called propyl. And so this would be octane, because it's 8 carbons, 4 propyl octane. So this list gives the names and formulas for the various alkyl groups that we could potentially use. And you can see that once you get past 2 carbons, there are even structural isomers for the alkyl group. So for the propyl, you can have a straight chain propyl, or you can have a propyl that attaches to the middle carbon. and those two have different names. One is N-propyl and the other is isopropyl. Now you're going to have to use flashcards again to remember these differences. The next one, the straight chain, is called N-butyl. The next one is an attachment of a straight chain, but not at the end carbon. So that's sec-butyl. The next is a side methyl group that makes it isobutyl. And then the last one is the most unusual one because you have the attachment in the middle carbon with 3 surrounding carbons, and that's called tert-butyl. Again, I'm used to doing this, and I've done this for a long time, so I remember these, but you will need to probably use flashcards in order to remind yourself of these various different ways that these alkyl groups can come together. All of these are fair game on a quiz or a test. Numbers are also used to show where on the main chain the alkyl group is attached. Alkyl groups never stand alone. So, as with the first example we named, we used the number 4 to show that the propyl was attached to the 4th carbon on the octane. So numbers are used to do that. Now, as it turns out, these sorts of compounds all have different boiling points, and they are removed from a mixture by means of what's known as fractional distillation. And fractional distillation is simply a way to remove compounds based on their boiling points. And as the compound has a lower and lower boiling point, it will go higher and higher in this thing, in this distillate, and be removed. This is what's known as a substitution reaction. A substitution reaction is a common reaction that alkanes undergo. This is a situation where the hydrogen is substituted by something else, in this case by a chlorine atom. And so you have ethane exposed to chlorine gas in the presence of either an energy source of either heat or light, and one of the chlorine atoms replaces a hydrogen, and you end up with chloroethane and hydrochloric acid. Now this is the simplest substitution reaction. Now the second major group, we've been talking about alkanes up to this point, Alkanes. The next major group is called the alkene, Ene. And the only difference between an alkane and an alkene is the presence of a double bond, of at least one double bond. Now there can be more than one double bond, but the presence of at least one double bond. So an alkene is unsaturated because the maximum number of hydrogens are not present. And so it's an unsaturated hydrocarbon molecule that it contains at least one double bond. So we have the expanded structure, the ball and stick structure and space filling model for the alkenes. Ethene, you'll notice it's Ene instead of Ane. Propene, and 1-butene. And the 1 tells you that the double bond is on the end and not in the middle. This results, as you remember back in the old, let me wiggle some really old neurons here. This results from a hybridization of the double bond C to sp2, and it bonds to a single sp3. Now you can polymerize ethene to form polyethylene. You probably heard that term. It's used to make plastic. By taking bunches of ethenes, exposing them to a catalyst, and then they will form this polyethylene that's shown on the right. Now here, the naming of an alkene is derived from the name of the corresponding alkane and just substituting the ene for ane. So ethane becomes ethene, propane becomes propene, butene, butane becomes 1-butene or 2-butene, depending on where the double bond is. And you'll notice that ethylene and propylene are also sometimes used. Butylene is not used. Now, there's a new kind of isomer that we have to introduce because of these double bonds, and this is called a geometric isomer. And geometric isomers occur in alkenes that have 4 or more carbons, so they can't happen in the 1 carbon or 2 carbon or 3 carbon situation. And it occurs if the double bond is somewhere in the middle of the molecule as opposed to one of the ends. And in that case, what you can see here is that in the middle, both CH3 groups are on the same side of the double bond, and on the right, the two CH3 groups are opposite each other. If they're on the same side, that's called cis. If they're on opposite sides, that's called trans. And so this is cis or trans geometric isomer for butene. So the one on the left, the one in the middle would be called cis-2-butene, and the one on the very right would be called trans-2-butene. A geometric isomer is where each of 2 or more compounds that differ from each other in the arrangement of groups with respect to a double bond, and also can be in respect to ring structures or other rigid structures, but we're introducing the concept here when we're talking about ring structures. I'm sorry, double bond structures. These models show this structural and geometric isomers of butene. Now, a substitution reaction that occurs with ethene, both chlorines will attach and form 1,2-chloroethane as opposed to the chloroethane plus hydrochloric acid. So this is the same substitution reaction, but in this case, both chlorines become attached to the hydrocarbon molecule. So here's another situation where you can have a substitution reaction, but first of all, let's name this guy on the left, and then we'll name the product. So first of all, see if you can figure out the name of this molecule on the left, and then write down the substituted molecule and then name that as well. Stop the video and work on that, and then restart the video and we'll go through that. Okay, the name here, it's 1, 2, 3, 4, 5, so it's pentane because it has a double bond, and all of the material is on the same side of that double bond, so it's cis-pentane, and it's at the 2nd and 3rd carbon, so it's cis-2-pentene. And then both these chlorines are going to come in and attach themselves, and so you're going to end up with 2,3-dichloropentane as the product. And that's shown right here. 2,3-dichloropentane is the resulting product once the reaction occurs.